So we continue with transformations of the complex plane as we now look at inversion. In the first two videos, we under these transformations of the complex plane, we had looked at reflection, which means z becoming z plus a. Then we looked at rotation and scaling in the other video, which is about z becoming az. Now we are looking at inversion. What is that about? Okay, so inversion is simply z becoming 1 over z. That's inverse. Z becoming 1 over z. So by definition, the inversion transformation in the complex plane is defined as z uh, being mapped to 1 over z, where z is not equal to 0, because if z becomes 0, this is undefined. So it maps each complex number to its multiplicative inverse. That is what inversion does here. So in the algebraic form, see what happens. So if you let z be x plus iy, then 1 over z is 1 over x plus iy, and then we can then uh we can rationalize. Yeah, that's what I was looking for. We can rationalize. Let me go and do that, right? Let me go and do that on the worksheet. So, z equals x plus iy, generally speaking, right? So uh for z becoming 1 over z, what happens? We say that 1 over z then is 1 over x plus iy. To rationalize, we then have 1 over x plus iy multiplied by x minus iy. We multiply top and bottom by the conjugate. And the rationale is that this divided by this is 1. And when you multiply something by 1, it remains the same, right? So that's basically the concept here. So by multiplying by x minus iy, of course, x minus iy, because it is the conjugate to this. So plus here, minus here, that means this is a conjugate. But then to balance it out, we multiply the numerator and denominator by the same x minus iy. So now we have 1 into x minus iy all over x plus iy into x minus iy. So don't forget 1 over z. So that's that's x minus iy now, all over x times x, x squared, x times minus iy, that's minus iy. That's x times minus iy, that's minus I xy, right? X times minus iy. Then next, plus iy times x, that's plus I xy. Then plus times minus, that's minus I times I squared, y times y, y squared. Of course, subsequently, we can just do difference of two squares. I'm going to show that soon. So 1 over z now is x minus iy, all over, of course, this goes. And then we have x squared minus I squared, y squared. So this 1 over z now equals x minus iy all over x squared. Then I squared is minus 1, right? Because I is square root of minus 1. So I squared is square root of minus 1 times square root of minus 1. So I squared now is um square root of minus 1 squared. So I squared is simply minus 1, like that. So this is minus into minus 1 y squared, so that 1 over z then becomes x minus iy all over x squared plus y squared. And then we can remove the rational, the real part from the imaginary part. So we have x over x squared plus y squared on one hand, minus I, then y over x squared plus y squared on the other part. So we have that, and then we can then collect these ones separately. That's the idea of inversion. So here we can then say x comma y is mapped to x over x squared plus y squared, comma minus y over x squared plus y squared. That's if you collect these two separately now, like I was trying to imply. Okay, so then we can also have the polar representation of inversion. So if you let z be r e raised per I theta, then 1 over z is 1 over r e raised per minus uh e raised per minus I theta. So, and the effect is that the magnitude is 1 over r, and then the angle is now minus theta. So the key properties for inversion include the following. Um, so it is not defined as z equals 0, of course, because it's 1 over z, right? If it is 0, it is undefined. Then self-inverse. So you can have the inverse of the inverse of z is z itself, right? So self-inverse gives z. Then mapping behavior, circles map to circles, lines map to circles or lines. That's what happens in this situation. And then you have the unit circle. So the unit circle, where absolute value of z equals 1, then maps to 1 over the absolute value of 1 over z, which is equal to z, and which is in a way still results to the unit circle, because if you take the moduli, you have modulus 1 over modulus z equals 1. So that's 1 over modulus z equals 1. That's simply modulus z is still equal to 1, so somewhat. Okay, so it's still the same thing, I suspect. Then example 1 here. So let z be 2 plus iy, I mean 2 plus I rather. Then 1 over z will be all of this 2 minus I all over 5, 2 over 5 minus 1 over 5I. Well, what we are saying is this, z is 2 plus I, okay? Uh, z is 2 plus I. So for z equals 2 plus I, then 1 over z is simply 1 over 2 plus I. That's what's happening there. And that means you have 1 over 2 plus I multiplied by 2 minus I, the conjugate of 2 plus I, all over 2 minus I. Then here, I don't have to waste time like I did before. So this is 1 into 2 minus I there. And then here, this is difference of 2 squared. That's 2 squares minus 2 squared minus I squared, basically, so that this is now 2 minus I all over 2 squared is 4 minus I squared is minus 1, like we know. So this is now 2 minus I all over 4 plus 1. That's 1 over z, right? So then that means we have 2 minus I all over 5. And then we can say this is 2 over 5 minus I into 1 over 5. So the real part, so we can say that xy is mapped to 2 over 5 comma 1 over 5 in that sense. That's what is happening on that page there. So that's what has happened here. That's why 2 over, we have 2 over 5 minus 1 over 5i. So in polar form still, if we let z be 2 e raised per I pi over 4, then we say 1 over z is 1 over 2 e raised per minus I pi over 4. So that's very straightforward. That saves a lot of time. Then we have for the circle now. So given that the absolute value of z equals to, this is a circle whose center is at 0 and the radius is 2, right? Then we say that 1 over root z is equal to 1 over, modulus of 1 over z rather is equal to 1 over modulus z, which is equal to 1 over 2, which is 1 over 2, right? Because the modulus of z is 2. So the circle then maps to 1 over 2. So modulus W now maps to 1 over 2. So we can visualize that using Python. So here we have, of course, we try to create grid and all that. And then we have z is x plus ij, y. So we avoid division by 0. And that's why we put this 1 e raised per minus 6. Then W now is 1 over z. Okay, so z is already declared here. So this is 1 over z. And then we try to do the plot down here. So this is the original plane. We see this is after we invert it like that. So in summary now, we have, imagine we have the original set. Circle not, if a circle does not go through the origin, the image will be, well, for Z mapped on to Z now. So circle not through the origin is mapped to a circle. Line through origin is mapped to circle through origin. Line through origin is mapped to line. Unit circle is mapped to itself. That was what we saw the other time, that, for absolute value of Z equals 1, right? So the inverse is absolute value of 1 over Z equals 1. So that's 1 over modulo Z equals 1. So it will be mapped to itself like that, because at the end of the day, 1 will still be equal to absolute value of Z, basically. So that's the deal we have in that situation. Yeah, I have, so okay, we still talk about connection to Möbius transformations. Interestingly, the next video we'll be looking at Möbius transformations. That'll be the last video under transformations of the in the complex plane. So for the Möbius transformations, we are going to be dealing with this kind of rational function, of course, dealing with complex functions. Now, f of z is az plus b over c is z plus d. These are this is the general form of the Möbius for Möbius transformations. Uh, for inversion, now we say f of z is 1 over z. So we then say, so if a is 0, so a is 0, b is 1, c is 1, and d is also 0 in this case for this condition to be met. So c has to be 1, a is 0, this will be gone, b is 1, it will be left, d is 0. So at the end of the day, f of z is 1 over z for inversion. So in summary, we have, but we are going to deal with Möbius transform. I think it should be Moebius or something like that when we get it looks like German. So in summary, we see that the transformation Z mapped 1 over to 1 over Z inverts distance from origin. It reflects angles. It maps circles and lines into each other and is conformal. So it is angle preserving except at Z equals 0. Except at Z equals 0, it is conformal. Conformal means it preserves angles. So now we have our usual 20 questions. So see the first 10 and deal with them. Of the first 10, I'll be answering 5. I'll be answering question 5. Show that the unit circle absolute value of z is invariant under inversion. That means that it is mapped to itself. Uh, feels that's like too cheap, but it's okay. We'll just go with it. I thought it was going to be challenging. Then 12 computes the inverse 1 over z, right? For z equals 3e I pi over 6, like that. So deal with this also. But let me take on questions 5 and 12, like I said. So for so we start with problem 5. Problem 5. We want to show to show to show that the unit circle, absolute value of z equals 1 is invariant, is invariant under inversion. I mean, invariance in a way means nothing changes even when you invert it. That's basically the idea of invariance. Okay, so here we say let absolute value of z be equal to 1, like we know. Then under inversion, right, absolute value of 1 over z is equal to 1 over, yeah, absolute value of 1 over z. Of course, okay, it's now 1 over absolute value of z. Okay, so if that is the case, since we already know that z is 1, right? So absolute value of 1 over z is now 1 over, this is already telling us this is 1. So that means 1 over absolute value of 1 over z is equal to 1. Yeah, we have that. So in essence, it's telling us absolute value of z is 1. Absolute value of 1 over z is also 1. Uh, we can say so absolute value of z is just the same thing as absolute value of 1 over z, which is equal to 1 in each case. And the idea of invariance is that if you like z, absolute value of z is 1, absolute value of 1 over z is also 1. That is, nothing changes when you invert a unit circle. Nothing actually changes. So it's basically the same. That's the idea of invariance. So hence the image of any point on the unit circle is also on the unit circle, right? So therefore the unit circle is invariant under the transformation z z maps to 1 over z, right? Therefore the unit circle, the unit circle is invariant under the transformation, under the transformation z mapped to 1 over z, like that. So that's 5. Now let's go for problem 12. Problem 12. So I go back to see that problem 12. Problem 12 says compute 1 over z for z equals 3e raised by I pi over 6. Okay, so to compute to compute 1 over z for z equals 3e raised by I pi over 6. So using the idea that 1 over z is equal to 1 over r e raised by minus I theta, what happens? So uh it means we have so we can say 1 over z now is 1 all over 3e raised by I pi over 6. So if that is the case, that means 1 over z now is equal to 1 over 3. So carving that out, then e raised by minus 1 over pi over 6. Yeah, we can let it go there, but we can actually take it to rectangular form. Rectangular form is the Cartesian, the XY axis kind of form. So this is okay like this in polar form. So this is okay like this in polar form already. So that it's that easy. But then on the other hand, we have so in rectangular form, what do we have? E raised to power e raised to power minus I pi over 6 is cos minus pi over 6 plus I sine minus pi over 6. By the way, pi is 180, pi over 6 is 30 degrees. And we know that cos is an even function. So whether it is cos pi over 6, it is the same thing when you have cos minus pi over 6. So nothing changes. And that's like cos 30, which is root 3 all over 2. Then on the other hand here, okay, let me go step by step. Because cos is an even function, cos minus pi over 6 is the same thing as cos pi over 6. Let's deal with that first. Then this is plus here. But sine is an odd function. So sine minus pi over 6 is the same thing as minus sine pi over 6. So because of that, now plus and minus comes in here, and we have I sine pi over 6. So that's the idea of an odd function. So the minus comes out, but this one swallows up the minus. So this is now like cos 30, which is root 3 over 2 minus I. Sine 30 is 1 over 2 easily. And then that goes. We can then say, thus, 1 over z now is simply 1 over 3 into root 3 over 2 minus I 1 over 2. If you tidy that up further, 1 over z now is root 3 over 6 minus I 1 over 6. And that's what we have. Or if you want to be finicky, if you still want to be finicky about this, 1 over z can still be 1 over 6 into root 3 minus I. You can still take it that far. All right, so with this, we come to the end of this interesting topic, uh, talking about transformations as with respect to inversion, that is z becoming 1 over z. We still have one more to go, talking about Möbius transformations in the next video. So watch out for that. Don't forget to try your hands on the 20 questions. You have the first 10 here, 20 practice problems. You have the first 10 right here to play with. And then I've done one of that. Then you have the next 10 here to lay your hands on. I've done one of that too. So you want to check it out and see how well you understand the gist. Let me know how helpful that is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. If you have not subscribed, I wonder what exactly you're waiting for. Why not go ahead and subscribe right away and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of the channel by clicking on join. That gives you special privileges like seeing some videos first or seeing some videos exclusively as a member of the channel, you can request for PDF copies of my notes. You can also ask for a hangout to discuss whatever interests you on my channel, all right? Whatever maths, data analysis, data science, and all that. Ultimately, don't forget to comment, like, share, so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.